From a distance, you might expect that there isn't much to see when looking at a black hole like Cygnus X1. However, black holes can be some of the brightest objects in the night sky. This is not due to the black hole itself emitting light, but is an indirect result of the effects the black hole has on the space around it. The bright lights that we see emanating from the regions around black holes are due to the material the black hole is feeding on, and from any material escaping from its mouth. If the black hole's gravity is so strong, how can some of this material escape? One of the first things we detect from Cygnus X1 are the radio waves and X-rays being produced from cone-like structures that seem to originate from the area around its rotational axis. These structures are called astrophysical jets, and they are one of the few structures associated with black holes that have been imaged directly. These cone-like structures can funnel material away from the black hole, and in the case of Cygnus X1, release the power of more than 1,000 suns. Astrophysical jets are thought to be powered by material falling onto the black hole, or another compact object. But the formation of jets is not yet fully understood. Imagine water cascading over a waterfall. The turbulence at the bottom and the resulting mist are analogous to the way jets are formed. We still don't know what jets are composed of, but leading theories suggest that they are either electrically neutral combinations of electrons, atomic nuclei and positrons, or a positron-electron plasma. This material is responsible for creating the light that we detect when we see jets. Near the inner edge of the accretion disk, hot material interacts with the magnetic fields generated within the disk. Due to these extreme conditions, not only is the material hot enough to be in a state of matter called plasma, but this plasma strongly interacts with magnetic fields to produce light in a process called synchrotron radiation. Although the precise mechanism of the interaction is still unknown, there is no doubt that huge amounts of energy escape from the infalling material in the form of a jet. In fact, there is so much energy within the escaping material that it can reach 10% of the speed of light. When this occurs, we say that the jets are relativistic. Relativistic jets can be seen emanating from compact objects like neutron stars and black holes. Jets originate at the magnetic poles of the compact objects and are, in general, aligned with the spin axis of the compact object. This is not always the case, however, as jets can be slightly offset from the spin axis. The magnetic poles of the Earth, for example, are offset from the rotational poles. This slight offset in jets can be observed as a wobble or a lighthouse effect. The lighthouse effect occurs as light from the jet sweeps across the field of view, just like light from a lighthouse sweeps past you as it rotates. While this effect can be seen in any type of compact object, including Cygnus X1, the lighthouse effect is more commonly associated with a class of neutron stars, known as pulsars. The jets from Cygnus X1 are 100 times longer than the distance between the Earth and our Sun when imaged in X-rays. On the other hand, if we look at the radio emission from Cygnus X1, there is evidence that the jets extend even further, possibly 600,000 times the distance between the Earth and our Sun. If a jet is not pointed towards us, the wobble can be seen through other effects. A good example can be seen in the relativistic jet originating from the elliptical galaxy M87. M87 contains one of the largest known supermassive black holes, which powers itself by devouring material at a rate equal to 1 solar mass every 10 years. M87's jet is a jaw-dropping 5,000 light-years in length, spanning more than 4% of its host galaxy. These NASA images of M87 show clear bends and kinks that come both from the wobble of the jets and from their interactions with material in the surrounding space. Since the material within a jet is travelling so quickly, we'd expect it to have features related to its motion, and indeed it does. Material from the jets is subject to the same Doppler shifts that we discussed in Module 1, which is evidenced by the fact that material travelling away from us appears to be redder and dimmer versus the brighter and bluer jets that are directed towards us. A good example of this was a recent survey by NASA Chandra Observatory of Pictar A, galaxy containing a supermassive black hole. NASA calls this black hole the Death Star because of the powerful beams of energy it generates. This is one of the best images we have of a complete system around a supermassive black hole. In this image, the central black hole of Pictar A is obscured by an intense X-ray source depicted by the colour blue, which is also the source of the jets. The blue jet that is visible on the right-hand side of the image is pointed roughly towards us, but the counterjet on the other side is pointed away. Due to Doppler shifting, we aren't able to see the counterjet. The red clouds labelled in this picture are also an important part of the environment around black holes. They are called radiolobes because they produce significant amounts of radio frequency radiation. We mentioned earlier that the size of the jet in M87 is more than 5,000 light-years long. The jets emanating from Pictar A have been estimated to be 800,000 light-years in length, more than 8 times the span of the entire Milky Way galaxy. With some jets from black holes exceeding the size of most galaxies, it's safe to say that some jets generated from black holes are among the biggest structures in our universe.